Hello, this is Jerry Woodall. I'm going to show you a demonstration of our technology in which we use aluminum to split water to make hydrogen as a fuel to run a utility vehicle in the internal combustion engine mode. Here comes the vehicle. As you will see as it goes by, it's being driven by one of the staff from the Herrick Laboratories. And in the back is a reactor that we designed to put the aluminum and add water to it. This is in a form of where the aluminum is alloyed with gallium. And so you see the utility vehicle circling around, and it's running just on hydrogen that's being generated by water that is splitting the aluminum that's dissolved into the gallium matrix that we have in this thing. I could put my nose on the exhaust system and breathe in the water vapor that comes out. Now I would like to introduce you to Dr. Go Choi. He was one of my last students while I was still at Purdue University. And he's going to give you a brief presentation of how the process works so you can understand the chemistry and the details of how this aluminum dissolved in gallium in the form of an alloy will split water into hydrogen and aluminum hydroxide.
Hi, my name is Go Choi. I work with Professor Woodall. We work on aluminum-based alloy as an energy storage material and for producing hydrogen. What you have just seen here is a vehicle powered by hydrogen, fueled by the aluminum alloy. Now I'm going to do a short demonstration showing you how this alloy can generate hydrogen. Now what I have here is the aluminum-based alloy. I also have a puddle of water. I'm going to drop this aluminum-based alloy into this puddle of water and generate hydrogen. So the bubble you're seeing here is the hydrogen being generated. Now, in the car, this hydrogen will be immediately captured and consumed for powering up the vehicle. So, now let's learn about the mechanism. This alloy is composed in two phases, solid phase and liquid phase. The solid phase is composed of aluminum. The liquid phase is composed of three different metals, gallium, indium, and tin. Now this liquid metal has an important role. It works as if it is a bridge. It allows the aluminum particle, the solid particles, to travel around and react with water to produce hydrogen. So let's look into this process in more detail. Now, let's imagine that the gold region represents aluminum. The gray color represents the liquid metal, gallium, indium, and tin. And the blue region represents the water. So, these aluminum particles flowing in the liquid metal near the surface will react with water and produce hydrogen. Now, to fill in the gap, the aluminum particles further apart from the surface will move toward the surface and also continue the reaction. Now, everything in this world has this tendency to restore equilibrium. To balance it out, the aluminum and the aluminum-rich grains will start diffusing into the liquid metal and move toward the surface and continue the reaction until all the aluminums are consumed. Now, you might be wondering, well, from the demonstration I just seen, I didn't see any liquid. Well, that's a very valid question. In fact, in our group, we work on several different composition alloys based on aluminum. Each composition differs depending on the application. For this particular alloy, even though you don't see liquid, inside the microscope, there are traces of liquid metal. Now, for example, in this picture, you'll see white traces of very thin lines. I'll color it up with red color. These lines represent where the liquid metals are. So, even though macroscopically you get to not see the liquid, microscopically there are liquid traces, which enables the reaction. Now, we learned about the mechanism. Let's move on to the economics. There are several reasons why we're interested in this alloy, but one of the biggest reasons is because its abundancy. For example, aluminum composes 8% of Earth's crust. In fact, it is the third most abundant material, the third most abundant element on Earth after oxygen and silicon. Also, we're interested in aluminum because it is recyclable. There are 400 billion kilograms of scrap aluminum or used aluminum lying on the surface. These scrap aluminum are sufficient enough to supply 12% of US annual use of energy. So because of this abundancy and recyclability, we're interested in using this alloy. Now let's look into the cost analysis. There are two markets that we're interested in. The primary market being substituting hydrogen tanks, the secondary market being the energy sector. Now let's talk about the primary market first. Producing hydrogen is actually very cheap. You can produce hydrogen from nuclear power plant or by using natural gas. However, the reason why hydrogen is so expensive is because of its storage and transportation process. For example, to store 1 gram of hydrogen, you need 600 gram tank. In other words, to have a certain amount of hydrogen that you want to store, the storage tank has to weigh 600 times more. Also, there are all other potential dangers, such as explosion, or because of the fact that you're storing hydrogen in high-pressure tank. There are many different difficulties. Now, what we would like to do is substitute this hydrogen tank with our system. We did some calculation. The current market shows that the hydrogen stored in hydrogen tank costs $100 per kilogram. We can generate the same amount of hydrogen with our system with the aluminum alloy at $9, which is almost 10 times cheaper. Now, another market we're looking into is the energy sector. Over here, I'm comparing with 3 different traditional energy sources, namely coal, natural gas, and gasoline. Now, the fourth bar represents our aluminum alloy, which costs a little bit more than 10 cents per kilowatt hour of energy. The cost analysis shows that although it's a little bit expensive, more expensive than the traditional energy source, they're almost in the close proximity. Now, I'm also going to make another comparison with another energy source or energy storage material, which is lithium ion battery. This analysis was done by a professor in Berkeley. According to his analysis, due to the fact that lithium ion battery having such a low energy density, the cost per kilowatt hour shows up to be 40 times more expensive than the traditional energy sources. This is why we believe that we have a potential to compete in this energy sector market as an energy storage material.